Okay, so last time we stopped over here. We have finally derived an equation. But one thing is that now we are gonna deal with simplifying it. Okay, so what I mean is that the final equation should be in terms of because we have so many variables. Okay, we have to clear away all these variables, so that eventually we can get an equation that is pretty much nice. Okay, because in terms of frequency. Okay, so we are still far from there. So let's continue, and then okay, so let's bring it out. Maybe I should do a, know, maybe a possibility. Okay, let's continue. So I've already drawn this thing clearly defined anyway. So since the point is not at the center of mass position, I mean the pivot. Okay, as you can see, the pivot is not at the center of the rod itself. What we need to do is to shift. Okay, we have to shift it to the center of mass. So one clear thing is that if it's in the center of mass, if the position is clearly at the center of mass, we no need to do this step. But however, since we are, you know, our pivot is over here, we need to do our parallel axis theorem. And so, let's write out the equation. Maybe I should use this color. So the equation is, maybe I pause up. Okay, so this is the equation for the center of the equation for the parallel axis theorem. This is your moment, if your axis of rotation pivot, your moment of inertia for when it is at the center of mass, when it is here. Our objective is to bring this thing over here so we can eventually continue our equation. So therefore, this is the position of our pivot over here. So we have plus certain mr square. So this is why we plus over here. We have a, we have a plus md square. So this d square is a distance between the two axes. Okay. So what do I mean by the distance between the two axes? It's just let's say, where's my pen? Sorry. So this is the rod itself. This is our pivot. So we have to move a certain distance to the center of mass over here. So this is the distance, the perpendicular distance between two axes. Okay, so what I mean is that between two axes, this is one axis, this is the second axis, two perpendicular axis lah. Then this is the distance. Okay, I mean d. So I bring this is the distance, I would say. But I don't know why is it d square, but let's just take it as, because I didn't derive this, so I don't know what the hell is this, but yeah, we just use this formula and we can eventually get that thing over there. So what do we do next is this. Hold on. Okay, so now we have to make assumptions. So after defining our parallel axis theorem, we have the equation over here. You have to know some assumptions. We assume, because the moment of inertia, okay, I naught has in terms of rod, in terms of the mass, okay, the relationship of the mass. But apparently we are talking about we are more concerned with the mass rather than the rod itself, because the rod is negligible. Yes, we don't assume that the rod itself has any mass, so therefore this whole thing becomes to zero. So just make sure that let you know that this I naught rod contains one equation, and I naught mass also contains one equation. I naught rod, okay, deals with the mass of the rod, okay, the mass of the rod. So apparently it's, as you can see, it's over here, but we don't care about the mass of the rod. We only care about the mass of the system, meaning the mass of this thing, and the relationship between this mass and the spring itself. Because if you add in the rod itself, as the assumption states, that it is pretty much negligible, because if your mass is too large, because the rod itself is just some light materials, meaning less density, so it's not heavy. So therefore we will assume that it's negligible. And to also make the math itself much easier to calculate. So yeah, so since we are talking about the I naught mass, which is the mg itself, and the relationship between mg and the spring, the reaction force of the spring, um, because you may also wonder, since we are talking about the rod, okay, since we are talking about the rod, then why you ignore the rod? There is two constitution of the system, okay, meaning um, the rod itself contains the weight of the rod itself plus the weight of the mass at this end. Okay, so there is two weight, the weight of the mass and the weight of the rod. But however, we don't want the weight of the rod because we say that the weight of the rod is pretty much negligible. So we only took hold of the weight of the mass. But however, their center of mass is always at this point because the pivot is here. So we have to move here in order to continue our equation over here. So hope you clearly understand what I mean. They share the same pivot, so this is why um, I don't care whether the rod or the mass, because they share the same pivot, we have to move the pivot. Since the pivot takes hold of the center of mass, we just move the center of mass to here. So I hope this clear a little. If I didn't clear, then that's not cool. Anyway, so where am I? So since we know the I naught mass, we're talking about the mass itself only, we're not talking about the rod. So let's fill in the equation. Okay. So this is as I say, ICM is equals to the center of the moment of inertia of the object. Okay, of the object. So we're talking about the mass itself. Okay, at the end of the rod. And then the d square is just the perpendicular distance from the pivot to the center of mass, some center of mass value lah. So you give me a while. Then we have this equation. So this portion is actually equivalent to this, and this is equivalent to this. So let me explain. So how do I get mr square? Okay, we do assume that the mass itself attached to the rod is taking this equation, the cylindrical shell with open ends, and then it's attached a point mass at the end of a rod of the length r. Okay, has the same moment of inertia. So apparently we assume this thing and we took mr square. So far I think this is much legit. Okay, I don't know, but yeah. And then plus mass times d square. Okay, some distance, 3r/4. So we are talking about this distance. Okay, from this point to this point, because the mass is over here, we have to bring this pivot to this portion. So I have my apology when I say that the mass is over here, but whatever. So yeah, so since you attach the mass, the center of mass is all at this point, so you just bring this point towards here. So bring this is it, and then to simplify the equation, maybe I pause the video a while. Hold on. So to simplify, we assume two assumptions. So for the first assumption, we assume that the length of the rod, okay, is much greater than the length of the point load. Okay, so what this means is that the length of the rod is L, right? This whole thing is L. But however, the point load of the mass is actually maybe hold on a while. I just draw. It's just this R. Okay, so apparently compared to L, R is actually quite negligible. So therefore R is equals to 0. Okay, since L is much greater than R. So this is the first assumption. Okay. The second assumption is hold on. Okay, so the second assumption is to assume small oscillation, meaning theta is lesser than 1 radian, which is very and that such that radian is also much smaller than 1 radian, which is like 0.05. So we one good technical tools is that this is hold on, yeah. So sine, if the angle in radian is very small, if you were to type sine 0.05, you will eventually get near to 0.05. Okay, so what I mean is that when you type sine 0.05 in terms of radian mode, you'll get 0.0499 something, okay? So it's eventually somewhat 0.05. So this is what I'm talking about. So the sine theta is actually approximately theta itself. Cosine theta is equals to 1, and then tangent theta is equals to approximately 0.05. You can test it out over here. I'm not going to do that. But with this assumption, then we can simplify this whole equation into a much easier equation. Okay, so you give me a minute now. So we have this equation over here. Let's simplify it. Okay, using this thing. Since we know that L is much greater than R, so R is equals to 0, then therefore this whole equation will become 0. And when theta is assumed to be very very small, 0.05, okay, so we can see for sine theta when 0.05 is equals to 1, approximately 1. So therefore this whole thing will becomes to 1. And therefore we have m, the mass of the mass itself, the load squared. Okay. So we have our initial, so we have finally solved for our this equation. I mean this portion over here. Okay, this I. Okay. So we have a hell lot of stuff over here and we solve for this only. So let's combine the equation first. Okay, let's combine the equation first. And give me a moment, magic. Okay, so once we sub in this I, since we say that I is part of this thing, because we are in fact finding this, we sub in into here, and we have this equation. However, since just now we say that our data is 0.05, so we just change these things. Okay, they're the same. We just change it to cosine 0.05 equals to approximately to 1. So we have this equation over here. Now another assumption comes in. Okay, this assumption is a little ridiculous, but I don't know how I'm gonna explain. But it talks about saying that unless explicitly specified, we know the g. Okay, so we don't care the gravity, and therefore this whole equation becomes 0. Okay, you're like what the fuck, right? Also like what the fuck. But I think that because mg itself, uh, this one is just the mass and the motion of the weight of the mass. That's all. Okay. And then as for here, it deals with the because our objective is actually find the frequency of the stuff. So we can actually say that because if you were to actually hold on so I don't know what to say. Okay, I may be wrong, but since we know that this is the summation of torque, as you can see over here in this equation, we expand it into this whole chunk over here. This is summation of a torque. But when this minus this, we have certain external forces that still continue to vibrate this whole equation, right? So we are much concerned on the because this would eventually contain the external force, the energy itself, and whatever stuff when you put it in. Okay. Um. Yeah, that's a little tricky. Okay, let's take this mass as an external force. Okay, and this thing as the movement of the spring. I mean the properties of the spring itself. So this is much important than this, I would say, because you want to find the frequency of the longitudinal frequency of the system, right? You have to find this k, I mean this whole system over here. So we are much concentrated on the system over here. Since we have already formulated this portion over here, we can actually ignore this sum for some reason. I also don't know what, but yeah, at least I think of it in the manner. And then it's equals to the certain vibration across these things. The data, that means along this axis, how it will vibrate. Okay, so it's just a relationship between the um the spring properties and the vibration. So because as we will treat this as an external force, we don't treat this as as I mentioned earlier just now, in the very early videos, when you have let's say you have a spring over here, when you pull it down and you let it go, okay, this you won't calculate how much force you pull it down, right? So I took it as a matter of fact. So when you put it down and then you release, the release of the thing is actually related to this the spring itself, and how it would oscillate. And then the oscillation will be described by its own equations. So apparently this is just an external force, and apparently they have so-called isolated external force as saying that gravity is zero, so everything is zero. So yeah, given that there is no resistance in air or whatever, so it's taking it as a very free vibration type of thing. It's a little complicated. So we will assume that this thing is like it will keep on oscillating, so we don't care about the G anymore. So I think this is by far I thought of it, but it's not a very strong intuition. But however, when you get this G is equals to 0, this whole thing will become 0, and you simplify this whole equation into this equation over here. Okay, and then after which we do some math. Hold on. Okay, I think I stop here. Okay, so actually I've written a lot of things. Anyway, so a quick browse through. Okay, so once we say that G is equal to 0, everything is equal to 0, and then we just bring this here, so we will have this equation, we just rearrange, and then to find the variables, so we have x in terms of x, and then in terms of data. So now since we have in terms of x, we need x to be data. So what is x itself is that x is actually um, the y-axis, okay, not this one. So apparently we need to find the x itself, the motion of the spring. If you remember, and then the distance that extends is x. So we are talking about this x itself. But however, this is in terms of data. So that's why we have to deal with L over 4 sine theta, because we are dealing with this portion only. As you can see, uh, after we deal with this, okay, because we're actually dealing with this portion instead of this portion, because this portion is already 0. So therefore we are concerned about the spring itself, the motion of the spring. So the x itself is actually the motion of the spring. It relates to the motion of the spring, and therefore it's L4 sine theta. And then we just sub it in. So this is the same as this. I just bring 9 over 16 out here, and then ml square, and then oh yeah, theta double dot. Okay, so plus KL over 4, and then x change to this equals to 0, and we have a homogeneous equation. Haven't yet. Okay, so since sine theta is approximate theta, as we can see, say that it's small oscillation, as we have mentioned earlier over here. Sine theta is approximate theta is when theta is equal to 0.05. So we can further simplify the sine theta equals to theta. So it's just one step over here. So we have this. And then we rearrange again, making the data double dot is coefficient equals to 1. So we have this thing. We just divide everything by 9 over 16 ml square. Okay, so we divide the whole equation throughout by this thing, we will get this one. Okay, it is KL4, this one multiplied by, when you divide it, you just invert. Okay, equals to 0, we have homogeneous equation. And then we compare. So if you remember last lesson, this is the equation we have derived, the equation between the mass, okay, the mass and the spring constant, okay, conservation of energy, the equation. So after you derive, after you use this, and then you use this equation, and then you solve for the second order differential equation in order to get your natural frequency equation. So therefore, we are also trying to find our natural frequency for this case. So we are actually, for this 24 and 25, we're actually finding natural frequency. So therefore, as you can see, the trend itself is the same. Mx double dot plus kx equals to 0. This is data double dot plus k over 9m data equals to 0. So you can see that k and m, when you so-called divide everything by m, you eventually get k over n omega. Square. Square root. A bit blur already. But for this case, it's about the same. So we already set it up. So imagine, okay, so if you don't get what I mean, and definitely you will not get what I mean. So let's say this is an x double dot. If you divide everything by m, you'll get k over m x equals to 0, right? And then this trend is actually same as this trend. So this is the same as this thing. It's just that 9m, now we are talking about 9m theta plus k theta equals to 0. It's the same thing, right? So now this is k over 9m square root. So this is why we have natural frequency over here. The same thing is just that the m itself has a coefficient of 9 in this case. I hope this is pretty much clear. And then let me see. So you may be wondering why suddenly we have this equation over there. Because if you were to multiply everything throughout, okay, if you multiply in, you rearrange the whole equation, you eventually get k over 9m. Okay, you just want to combine everything into one term. But however, this 9m belongs to here somewhat, so that you can have this equation correspondingly. So therefore, we have k over 9m as our natural frequency for the whole system. Okay, as for this system, okay. And then since t is equals to 2 pi over the period itself is equals to 2 pi over the natural frequency, and it's also equals to 1 over the longitudinal frequency. You can just flip it out. Okay, just flip it out, then 1 over 2 pi the natural frequency. So we will have this answer over here. And I hope it's pretty much clear. And yeah. So next video I'll just summarize everything, and then that's it.